Because of the size of the files that these videos generate, I'll be breaking this one up into several files. This is the Jamestown Steel Company example for the hypothesis test, and in this example the company manufactures and assembles desks and other equipment. The weekly production of the Model A325 desk at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. Recently, new production methods have been introduced and new employees hired. The Vice President of Manufacturing would like to investigate whether there has been a change in the weekly production of the Model A325 desk. A sample of the last 50 weeks yields a sample mean of 203.5 desks. Use the 0.01 level of significance. So let's look at what we have underlined here. We have the population mean of 200 and the population standard deviation of 16. Because we know the mean and the standard deviation, we can go down here right to step 3 and determine which statistical test to use. So we know that that is a z-test because both the population mean and standard deviation are known. We also see the underlined portion that there has been a change in the weekly production of the Model A325 desk. A sample of the last 50 weeks and a sample mean of 203.5. So the change, it's not saying has there been an increase or a decrease in the weekly production, which would indicate a one-tailed test. It just says change, so that indicates a two-tailed test that we're going to do. And the sample of the last 50 weeks is our n, the mean is our sample mean, and we're given our 0.01 level of significance. So let's go ahead and put that in right away. So there we have steps 2 and steps 3 filled out. We'll take a break. Picking up where we left off, we need to figure out what is our null hypothesis and the alternate hypothesis. So the null hypothesis, assuming that there's nothing going on, our h sub 0, which I won't bother to put as a sub, is that the mu is equal to 200. In other words, we think that the population distribution or population mean is 200. The average weekly production is not different from 200 desks per week. Now our alternate hypothesis is that the mu is not equal to 200. And we'll just cheat a little. Copy that down. It's not different from 200. Or excuse me, is the average weekly production is different from 200 desks per week. We have our significance level. We now have our null hypothesis and our alternate hypothesis. And remember, what we're doing with this test is we're seeing if we are going to nullify the null hypothesis. So now we have to do step 4, formulate the decision criteria for when to reject the null hypothesis. We're at step 4, formulate the decision criteria for when to reject the null hypothesis. Based on our alternative hypothesis, HA, of mu is not equal to 200, I don't know exactly what's going on here. We reject H0, or the null hypothesis, if our test Z, or the absolute value of our test Z, is greater than the z critical value that we're going to determine. Since the alpha is equal to 0.01, our z critical value is equal to the z of the alpha divided by 2. Why is it divided by 2? Because we have a two-tailed test. And this thing just keeps wigging out and giving me strange font sizes. I'll reduce this down just for the one so you can see that it's supposed to be a subscript. And that is equal to a z value of 0.01 divided by 2, which is equal to a z value of 0.005. And again, these are all subscripts. I'll reduce them down so it looks a little bit clearer. Okay, the area between the tails, if the tails are each 0.005, then the two of them together are 0.01, which means that the remainder of the area is 0.99. The rejection areas then are based on 0.500, which is half of the probability of the distribution, since that's what our table gives us, minus the 0.0050, because we're trying to determine where our critical value lies, and that becomes 0.4950. And then if we see table B1, B1 will give us the closest value to 0.4950 is actually 0.4951, and that gives us a corresponding z value of 2.58. So our z critical value is equal to 2.58. Actually, we would have two t critical values, or z critical values, and those are going to be negative 2.58 and plus 2.58 because we have a two-tailed test. So we can have our reject statement if, and that's actually H0, if the test z statistic, the absolute value of the test z statistic is greater than 2.58. It also could be stated as reject H0 if the z is less than negative 2.58 or the z is greater than plus 2.58, but you don't have to put the plus sign in there. Or it could be stated as reject H0 if z is not between negative 2.58 and plus 2.58. And there's our decision criteria for when to reject the null. We can also use Megastat to calculate our critical values for us. We go to Megastat, go down to probability, make sure you select the appropriate distribution, because in this chapter we're using both the t-distribution and the normal distribution. For the Jamestown example, it's the normal distribution because it's the z value we're looking for. We select calculate the z given the p. We select a two-tailed test. You can show the access points, show the inner center line if you want to put that stuff in there. Here's a pattern, kind of gives you an indication of where the critical values are. And we put in our mean, which in this case is 203.5 desks, and our standard deviation is 16. We click OK, and Megastat formats it nicely for you. Here's your plus 2.58 and your negative 2.58 critical values. The one thing to note is that it seems that when you're doing the probability distributions, if you go back into Megastat and change something and do it again, it does not create another one, it just writes right over top of this. Normally when Megastat does stuff, it just keeps dumping it lower and lower onto the spreadsheet, but it doesn't seem to do that with this, so be careful of that. Now that we have our decision criteria, we go down to step 5. And in step 5, this is where we look at, well, how likely was it that we got what we got, or what did we get in our sample, and then how likely was it what we got, and if it's very unlikely, we'll call baloney on the assumption that there is nothing going on with the null hypothesis. So we have the values here. The mean the population mean is 200. Our sample mean is 203.5. Our standard deviation for the population is 16, and our n is 50 desks. So we know we know now that the test is a z-test that we're doing. So we can just punch in the formula. Here's the t-test, here's the z-test. It's provided for us. That's actually an equal sign, not a plus sign. I like to use the parentheses to make sure I'm not missing anything. So we want the x bar minus the mu divided by the standard deviation divided by the square root of n, close it out with our two closed parentheses, and we get 1.5468. If we brought that down to just 2 decimal places, it would be 1.55. So now we compare the test statistic to the critical value and determine whether or not that's going to be, does it fall within the range or does it not. Because the z value of 1.55 does fall in the rejection region, we fail to reject the null hypothesis because we conclude that the population mean is not different from 200 at the 0.01 level of significance. So we would report to the president of manufacturing, notice that this is hidden here, that the sample evidence does not show that the production rate at the plant has changed from 200 per week.